Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah. We continue our class. Tonight is the last class for this year, but not the last class for this lecture series of lectures. And I've stopped at this slide last week, and this is actually the most accurate presentation so far of our universe. This is the map of our universe, and every point here, every point, blue points here, is a supercluster of galaxy. So superclusters of galaxies scattered all over the universe. There are of course gaps here because they use radio telescopes, and those radio telescopes still not map these dark parts here, right? But it's basically what you call it as our whole universe, our whole observable universe, with all the superclusters of galaxies scattered quite evenly over throughout our observable universe. Okay, now I started with all these things because we need to have an idea on how our universe looks like and how it comes about. How it looks like. Before we discuss on how it comes about, how it becomes like this, right? We need to have some sense of how huge our universe is and the content of our universe. The most surprising thing about our universe, even though it is huge, right? Even though there are multitude of objects inside there, but as what Einstein said, the most surprising thing about our universe is that it is understandable, right? It can be worked out quite simply. It is not that complex. That is the most surprising thing about our universe, right? We can apply our simple physical laws or whatever physical laws that we discovered here on Earth, and we apply it out there, and we get the same result so far. I said so far because we do not know in the future. And so far, what we can see, what we the map of our universe, the representation of universe, like as in this slide here, right? It is what happens those billions of millions and billions of years ago, because we know, and I've shared a number of times before, that this universe is so huge that it will take years, thousands of years, millions of years, sometimes billions of years for the light to reach our eyes. So what we can see on the furthest reaches of our universe here are those galaxies or those objects, right? That what do you call it? Escape from that object, the light escaped from that object billions of years ago and just recently reached our eye. So therefore, we actually do not know what is happening out there right now. Right, this is the map of the universe as it is according to what we can observe. Currently, we do not know because we are looking at the past. Right now, one thing about the universe that has been agreed upon by all observers, by all astronomers and scientists, is that this universe is currently expanding. It is not a static universe. What we can see in this map here, right, in this slide here, right, it is currently like that, but it is expanding. But of course, you can't expect it to expand so fast, right? As if tomorrow and then a year after that, you see that this map can be changed and it gets bigger and bigger. No, right? Because this is the whole cross universe, and it's expanding at a very fast rate, right? But because this universe is so huge, right, it is as if it remains static. Just like when we look up there, right, the stars up there, we see the stars are not moving; they are fixed stars. We can see some stars move. Those are either what do you call it, planets or satellites orbiting around us, orbiting around Earth. But planets are moving, and they call it as wandering stars, but they are not stars. But when you look at the stars out there, the fixed stars, they are not moving. What we see right now, right, is almost the same as what our forefathers see 100, 200, 300 years ago. The stars remain fixed like that. But we know that the stars are actually moving. It's orbiting around each other, it's orbiting around its own galaxy, and so forth and so forth. Right? So it's moving. But how come we cannot perceive that movement? How come the stars are all like fixed up there? It is because of the huge distance from those stars and us. And because of those huge distance, the movement of the stars, even though those movements, they are fast, but because it's so far away, it is as if the stars remain niche stationary. So as it is, our universe like this. But our universe is expanding. Okay, that is the fact that is been accepted. Now, when you talk about the universe expanding, this is page 55 of my book, right? The first person to discover that the universe is expanding is this astronomer by the name of Edwin Hubble. He's a very famous astronomer. His name Hubble is being used for many, many things. One of it is the space telescopes being sent out there. And I shared with you about the Hubble Telescope, right? Launched by NASA in I think 1989, and still functioning right now, right? Still contributing to our knowledge of the universe. So Edwin Hubble in 1920s, right? When he looked up there in the through the telescope in California, he discovered that those galaxies, very far, far galaxies out there, are actually moving away from us at a very high speed. And he calculated, and he found out that those speeds of those distant objects, right, flying away from us, right, in excess of almost 40,000 kilometers in 1 second. Imagine 40,000 kilometers in 1 second. The speed or the velocity of our sun orbiting around our Milky Way galaxy is just 270 kilometers in 1 second. But these distant galaxies, they are moving away at a very fast, high speed from us at 40,000 kilometers per second. So we are just like in the center, and everywhere that he look, all those galaxies surrounding us, right, very, very far galaxies, they are accelerating, or they are, we can see, accelerating away from us at a very, very high speed at 40,000 kilometers. And when he discovered that these distant objects, uh, galaxies, right, moving at a very fast speed, it actually conforms or proved the theory that Einstein proposed before that in 1905 and 1915. He proposed a theory of special theory of relativity and general theory of relativity. And according to his equations, the universe must be expanding. Uh, but somehow or other, he didn't like the notion that this universe is expanding. He was of the old philosophical school that this universe is actually fixed from the moment of creation and eternal, right? And we never change. So he changed his equation and he put inside some constant to make his equation as if shows that the universe is static, and he did that deliberately because of his own philosophical ideas, right? But then when Hubble discovered that the universe is actually, the stars are all, I mean, not the universe, I mean, the stars are all receding from us, the distant objects, distant galaxies are all accelerating away from us. And when he looked back at the original equation of Einstein, that equation of Einstein, those field equations of Einstein conform to that phenomena that he was observing. So Einstein, when he knew about this, he regretted very much. One of his biggest regret, right, is to change his equation to conform to his own philosophical ideas. He should just, he said, just let the equation stand by itself and tell us what it is all about. So his equation originally predict the expansion of the universe. Now, there was Edwin Hubble in 1920s. And now, right, we have discovered distant objects, and we call them as quasars. Right? And these distant objects, they are receding, they are flying away from us at an excess speed of 270,000 kilometers in a second. Imagine, that is 90% of the speed of light. So these distant objects are flying away from us at zero point 0.9 speed of light. And we know that the speed of light is the maximum speed limit in this universe. Allah has set that limit, right? Why is that speed limit at at speed of light? We do not know, but Allah has set the parameters of this universe that the, what they call it, the greatest speed possible is the speed of light. You cannot go beyond the speed of light, right? So these objects, you call it as quasars, uh, flying away from us at 0.9 speed of light, or 90% the speed of light. Now, what are these quasars? Is still speculation, right? But there is this, what do you call it, a very high suspicion that these quasars are actually early galaxies. These, we call it primordial galaxies. Those galaxies that were initially formed when this universe was still relatively young. And these quasars, right, they are so distant and yet they are very bright. They are very bright. So it means that this early, if they are true, if this theory is true that these quasars are just early galaxies, then these early galaxies, they are very bright objects. They were, or they are, up to you. You can use whatever tense that you want, right? They are bright objects, very, very bright objects. Imagine how far is that quasars from us? The most distant quasar from us is around 13.8 billion light years away. 13.8 billion light years away. In other words, when we look at that quasar, the light from that quasar escaped from that quasar itself at 13.8 billion years ago. So far distance, right? In the past. Our sun formed about 4.5, 4.6 billion years ago, just 4.5, 4.6. And this light, right, has escaped from that object before even solar system was formed. It escaped from that object even before the initial star that caused the formation of solar system was even formed. That that far, how far that object is from us. And yet, all this light has been traveling 13.8 billion years all the way, right? And it escaped there. Our sun is still not formed yet, and then the sun is still forming, right? And then our planets were there, right? All the planets rotating, orbiting around the sun, right? They were formed, and still this light is still traveling. And until now, right, when humans are here on this planet Earth, the light just reached us. That is how far that object is. And that object is moving away, flying away from us at 90% speed of light. So if you can imagine, right, in a distant future, these quasars will be so far away from us that we can't observe it anymore. It will disappear from our view. How is that so? I will explain later, right? But the thing is this: the universe is expanding, right? And everything is receding from us at very, very fast speed. The further the object is from us, the faster the object is racing away from us. The nearer an object is, a star or galaxy, whatever, to us, all right? Galaxies, I'm talking about galaxies. The nearer galaxies, the galaxy is to us, right? The slower will be the velocity of it receding away from us. As it gets further and further away from us, it gets faster and faster. So then we said, why is that so? All right. So astronomers, right, scientists have been pondering and thinking about it, and they're looking at all the theories being put forth and tested all those theories, and ultimately they have reached most of the astronomers, majority of them. I don't say all of them because there are always, of course, different views, right? But those are the minorities. The majority of astronomers believe in this theory. They accept this theory of expanding space, right? Now, how to do that? First of all, the question being asked usually is that how do astronomers know that these objects, these stars are, running away from us or receding away from us at a very high speed, and what is that speed? How do you know, right, that these stars are moving away from us, whereas these stars are almost fixed? The answer lies in what is called as Doppler effect. And Doppler effect is the effect of sound, right? If you know an approaching train or approaching car, when it comes to you, or let's say ambulance, or police car, when it is approaching you, you hear a very high pitched sound. Toon. And then when after that car passed over you and receding from you, you are going back and it's moving away, the sound, the pitch of the sound becomes lesser. So instead of high pitch sound, it becomes low pitch sound. It becomes just like that, right? So an approaching sound has a high pitch sound, a receding sound has a low pitch sound. So it's like boom, like that. So a car approaching you will be, the sound it makes will be like boom, and then after it passes you and receding back from you, right? And the sound change to very low grumble sound. Now that is a Doppler effect for sound, right? Light, because light is also a wave, light also has a Doppler effect. Now, what is a Doppler effect? Some of you might remember it, some of you might forget it, but just to refresh ourselves, everything that produce that has what do you call it, wave-like structure, right? If it produces wave and if it moves, the direction towards its direction of its I mean the wave that is towards its direction will be compressed, just like this. Will be compressed. Because why? Because the wave is receding, is moving away from the object, but that object is racing towards the wave, so it is actually compressing the wave at the back. Whereas behind that object, right, the wave is moving away from the object, and the object is also moving away from the wave that it produced. So therefore, the wavelength, right, of the wave is being stretched further and further. So it's just like a spring, right? You push the spring over here, the spring will compress, and yet it will pull away the spring over there. So the spring over here will get extended. So that is actually Doppler effect. So if it is sound, then over here you will see a high pitch sound, and over here you will see a low pitch sound, right? Low grumble, we call it. So if you're here, then you will see the original, you will hear the original sound. So that is Doppler effect for sound. And light is also the same, because light it consists of waves, right? If an object is moving away, right, is moving towards this direction, then it's compressing on the blue spectrum of the light. Whereas if it is receding away from you, it is stretching away the wavelength, then it is pulling away, it is pulling the red part of the spectrum. You know, spectrum is the seven colors of the rainbow, right? White light consists of seven colors all mixed together and becomes white. But if you break it up with prism, and then you can see all the seven lights, that's why you have those rainbow. So, subhanallah, see, Allah created these seven colors mixed together and becomes white. We cannot perceive these seven colors because they are in between a small narrow of wavelengths that our eyes can only see as one wavelength, and therefore we see as white light. But if, let's say, for example, Allah create our eyes with greater clarity, with greater precision, then we can actually see all the breakup of those lights, just like, you know, human-made lens. When you have a glass, right, lens, and then you point it in a certain angle, then the light will broken up into seven colors. So this spectrum of light is very useful for us. Subhanallah, Allah create this spectrum of light, just a few what do you call it, wavelengths in size, right? But it contains so much information that from this just visible spectrum, we can actually discover the contents of all other objects in this universe, all the stars and galaxies. And not just that, from this visible spectrum, we can actually calculate the speed of that object, the velocity of that object, whether it is moving away from us or towards us, just by looking at its visible spectrum, subhanAllah. Whereas this electromagnetic spectrum is just not just the visible spectrum. Beyond the red light here, you have the infrared, and then you have the what do you call it, the radio waves. Beyond the blue light here, we have this violet here, and then we have ultraviolet wave, and then we have this X-rays, and then we have gamma rays, and all those dangerous rays. So this part of the spectrum, sorry, this part of wavelength from the electromagnetic spectrum, right? Beyond ultraviolet, beyond violet itself, the ultraviolet, all these rays are dangerous to us. It can destroy our cells. Whereas these rays here, right, the wavelengths beyond red, we have infrared, and then we have radio waves. They are quite harmless to us. Yes, of course, infrared can cause burn, right, because it's hot, right, but it will not burn us straight away, right? And radio waves will not do anything to us, because why? Because the wavelengths are bigger, so therefore they pass us easily, and it carries less energy. Whereas those rays beyond ultraviolet, the wavelengths are shorter, right? When the wavelengths are shorter, it carries more energy. When it carries more energy, it can destroy our cells easily. So X-rays can kill us, cosmic rays can kill us, ultraviolet can cause us sunburn, and so forth. Now, if you understand this, right, Doppler effect for light, now, we have to go back to what is Doppler effect for light when when they use it to like I said just now, to find out the velocity of those objects out there, galaxies, whether it's moving away or moving towards us. They use it, or they call it as redshift or blue shift. If it is moving away from us, we call that object as redshifted. If it's moving towards us, we call it as blue shifted. Because why? Because the blue part of the spectrum has smaller wavelengths, whereas the red part of the spectrum has bigger wavelengths. And if the object is moving towards us, it means that the light that reaches us will be compressed. So therefore, it will be bluer. So that's blue shifted. But if the object is moving away, if you are here, right here, and the object is moving away from us, and so that object is stretching its wavelength of light reaching us, so therefore more red light will reach us rather than blue light, right? And so therefore we said it is red shifted, because red spectrum has longer wavelengths than the blue part of the spectrum itself. So this is what is called as blue shift if it's moving towards us, red shift if it is moving away from us. So we are here. If you are here, observer here, then we see this star or this galaxy is red shifted because moving away from us. But if you are here, right, and we see this galaxy is moving towards us, we see that the light is being compressed, so therefore it is blue shifted. So this is basically the Doppler effect for light, whether red shifted or blue shifted. Now, how do you measure the speed from redshift or blue shift? This is another information that Allah has given us, right? Allah opens up the door of knowledge, and Allah has created all the rules for us to discover, right? Without going to the star or the galaxies themselves and observe them, we can just look at the light that reach our eyes and reach our telescopes, and we break it up into the visible spectrum, and then we analyze this spectrum of light that came from that galaxy. And when we analyzed it, we found out that there are actually black lines. It's not just beautiful spectrum like this. This you can see if you use a very crude prism and then we break it up just like that. But if you use a precise, a very good instrument, right, that can measure the spectrum, we actually can see black lines across the spectrum. These black lines actually represent elements that uh, that were burned, or the elements that were burned and emit that light. Let's say, for example, you have an aluminium, pure aluminium, then you burn it. Of course, you produce light, right? It becomes white. So that light, if you capture it in a spectroscopy, they call it spectroscopy, because it measures the spectrum, and you can see that the light actually being broken up into a spectrum from red to blue. And furthermore than that, you can see black lines started to appear. It's just like barcodes, you know. So For aluminium, there are several black lines that is very unique for aluminium. If you burn, for example, carbon, you produce another black lines unique for carbon. So therefore, right, Allah subhanahu wa ta'ala has created, in other words, in crude terms, Allah subhanahu wa ta'ala has created barcodes, or QR codes if you want to, but there's no QR codes, it's barcodes, a unique identification for every single element there is in this universe. You burn that element, it will produce its own barcode on that spectrum. So therefore, when astronomers capture a light from a galaxy, from a star, right, and break it up into a spectroscopy, then black lines started to appear. From that black lines, which represent, right, elements of this periodic table, scientists can actually know that star contains what elements, which elements is in that star. And not just that star, any objects that emit light, or light that came out from that object out there, we can break it up and look at the barcodes, the unique identification of those elements. And if that barcode is there, then it represents, or it shows that that element exists in that far distant object in space. Subhanallah. So that is why, you see, astronomers, when they look up at stars, they know the content of the stars. These stars is iron rich, or there's not much iron, there's a lot of hydrogen, helium, carbon, whatever, from the barcodes of the spectrum of the stars. When they look at Jupiter, for example, right, we do not have to go to Jupiter and take a sample of the air and analyze the gas test to see what gas is Jupiter has, right? We don't have to do that. We just look at the light from Jupiter, and we look at the signature barcodes of that spectrum of Jupiter's light, and from there we know already what elements are in planet Jupiter from that unique barcode of elements. So subhanallah, that is what Allah subhanahu wa ta'ala has given us, all this ni'mah. That's why Allah subhanahu wa ta'ala says in the Quran that Allah subhanahu wa ta'ala has made things easy for us, everything in this world and up there, the skies there. Allah has made things easy for us to calculate, right, to measure, right, to know the content, right, to know the speed, right, from just the light that reaches us. That is knowledge Allah SWT has bestowed upon us. Subhanallah, alhamdulillah. So, if let's say, for example, right, the light that being emitted from an object, right, produce these signature black lines, these signature barcodes. But then, right, the same light that comes from the star that contains the same elements, right, will have this barcode actually shifted to the right here, shifted a little bit to the right. When it's being shifted to the right, it means that the star itself is actually moving away from us. Because why? Because it is pulling away the wavelength. It is not compressing the wavelength and make the wavelength shorter so that it becomes blue, but it's pulling away the wavelength, right? Just like the spring, you pull away the spring so that the waves becomes longer and longer. So when the waves become longer and longer, the wavelength, so it becomes redder. So it's being shifted to the red. This is what red shift is all about. Is the black line is actually shifted towards the red end of the spectrum. That is nearby star. If you go to a nearby galaxy, let's say, for example, Andromeda Galaxy, you have M16 and so forth, right? All these galaxies in our local cluster, right? And it is moving away from us, right? We can see that the shift is getting more and more towards the red. This is the original reference point, but nearby galaxy is moving a little bit further than the star. Why? Because this galaxy is, of course, further than the star. And we look at distant galaxy, right? As you look at a more and more distant object, these signature black lines actually shift more to the red end of the spectrum. And if it's a very distant galaxy like quasars, then the whole spectrum, these two lines, 1, 2, 3, 1, 2, 3, and 4 lines here being shifted towards the green and the yellow part. It's leaving the blue part. and this line here actually disappears. So the whole barcode actually shifted more towards the red end of the spectrum. So we say that it is redshifted. No, it is very much redshifted, right? A very large redshift compared to a star, which is shifted but not that much. Redshifted not that much, but very distant galaxy is shifted very much to the red. It means that from this, right, movement of this black line towards the red, compared to the original reference uh, black line here from laboratory, the distance that it shifts can actually be calculated by equation, and from there it can generate actually the velocity of that object receding away from us, just from there. But if this black line here shift towards the blue, and if this, you see this last black line here moving towards the blue, then we can calculate actually how much that object is moving towards us just from the shift itself. And so therefore Edwin Hubble, right, when he pondered, he looked up there and he saw all those distance galaxies receding away, right, and he used the spectroscopy and then look at all these signature black lines. From there he calculated the velocity of that object. That was his genius, right? He what do you call it, devised the equation to calculate the velocity of that object just from the shift of that black lines in the spectrum. So that's why he found out that, well, all these far distant galaxies, they are racing away from us at 40,000 kilometers in a second from their redshift. And right now we know that quasars moving at 270 kilometers, 270,000 kilometers, 270, 100,000, 270,000 kilometers in a second, racing away from us. So this universe is actually expanding, right? All these objects are racing away from us. So currently, right, we are in a moment where we look up there, right? This universe basically is getting bigger and bigger. Now, why is it actually expanding? We use this analogy of a balloon, right? Originally, the balloon is small, and then you have points object of there, right? Okay, let's imagine that the surface of the balloon is our space-time frame, right? And all our all our galaxies are on the surface of the balloon, right? And they are fixed point there, fixed point. Then you just have a balloon and just put dots here and there, and all this one of these dots represent, let's say, galaxies. Then you blow into the balloon and the balloon gets bigger and bigger. And as the balloon gets bigger and bigger, the space between all these points that you put on the balloon will get bigger and bigger. And so you can see that the points, right, on the balloon is actually getting further and further away from each other. If, let's say, there's an observer on this point, when he looks at the other point and the balloon is expanding, he is looking at that point racing away from him. Because why? Because this point is racing away from him and he is also racing away from that point. So it is actually accelerating. As the balloon gets bigger and bigger, every observer on this point will see the other points, right, racing away from it, because it is getting further and further away from that point, and that point is also getting further and further away from that observer. So ultimately, as the universe gets bigger and bigger, right, all these galaxies are fixed there, but because the space itself is expanding, space itself is expanding. What causes the expansion? There are theories that I can discuss later on, right? But the space itself is expanding, and therefore these galaxies in between the space, right, will race away from each other. And as space gets bigger and bigger, the 2 points, right, will get further and further away and faster and faster away from us. Because you see, if let's say you have 1 point here and 1 point here, right, it's very far. And as the balloon starts to expand, right, this galaxy here will race away from this galaxy, and this galaxy will race away from that galaxy, right, at a very high speed. The bigger the balloon gets, the faster will be the speed that these two galaxies racing away from each other, because they are very far. But if, let's say, right, the galaxy is nearby from here to here, right, it's still expanding, but you can't see this, this galaxy will not be moving away at a very high speed from this galaxy. Why? Because the distance between them is not that big. So just imagine you have 2 points, right? Like this and like this. If these 2 points, right, is quite close together and the space in between them is expanding, right, and the space between them is very small, is limited, so therefore the addition of space in between them is not that much. So therefore these two objects is moving away at a slower speed. But if you have two objects further away from each other, right, further away from each other, the space in between them is a lot. And if every point in this space in between them is expanding, so therefore the rate of expansion is greater. So therefore these two objects will race away from each other at a greater speed rather than the two objects that are smaller, right? So you just fill in, right, the space in between them. So if the space between them is small, then you can't fill a lot. So therefore it's expanding slower. But if the space between them is bigger, you can fill in a lot more at the same time. So therefore these two objects will race away from each other very fast, and therefore the speed in relation to each other is very fast. So let's say if this is Earth, right? And this is a nearby galaxy because the space between them is not that much and it's expanding, right? So therefore, the speed, the rate of expansion, the speed that is both of them are receding from each other is slower. So this observer on Earth will see that this galaxy is moving away from it, yes, but because it is also, he's also receding away from the galaxy, so you have double the speed, but it's still slower. But if you have a very far distance here, then you have this observer here on Earth and you have this distant galaxy here, because there's so much space in between them and every point of this space is expanding. So therefore, right, the space is expanding at a very high rate, greater rate than the one that is smaller. So this observer looks at this galaxy is moving very fast away, very fast, very high velocity from that observer, and he is also actually moving very fast speed from that galaxy, and in total we have both of them receding away at a very high speed. And that is why, right, when astronomers look up there at space, when they look at very distant object, they see that all these distant object, the more distant the object is from us, the greater the speed it is running away or racing away from us. When the object is nearer to us, then the speed that it races away from us is slower, receding from us slower. So that is the reason why further objects, right, it is moving away further and further away from us at a very high speed. And if we reach a point where the space that expands is getting bigger and bigger, right? And therefore the rate of expansion between these two objects is so huge that this object is racing away from this object and this object is racing away from this object at more than the speed of light. When it reaches the speed of light, at that moment of time, when it reaches the speed of light, the receding velocity, it reaches the speed of light, the light from this object cannot reach this object, this observer on Earth. And beyond that, if it gets faster and faster, because it's getting, further and further away, so more space expands between them. So therefore, the speed of recession, right, getting away from each other is more than the speed of light. And when it's getting further and further away, more than the speed of light, this object will be invisible to observer on Earth. you cannot see this object anymore. This object still there, but the light cannot reach us because why? Because the light can travel only at the speed of light, whereas this galaxy, right, it is not moving actually. It's actually not moving, but the space is pushing it away, right, from us, and the rate of pushing away is greater than the speed of light. So therefore, light cannot reach the observer on Earth. And so this object is invisible. And so therefore, right, many astronomers believe that what we can observe out there, right, the furthest quasar, the furthest object that we can see is about 13.8, 14 billion years away. That is the furthest object that we can observe, and beyond that, we cannot observe anymore. Beyond that distance, we cannot observe anymore because that galaxy, from our perspective, will be racing away from us at greater speed than the speed of light. And we will remain invisible forever and ever. So this light here, right, represents the whole observable universe. And our universe is not just this actually. Our universe is bigger than this because it actually encompasses all those objects that are beyond our observation. There might be stars, galaxies away, right, receding away from us because it's so far from us, right? It is receding away from us at greater speed than the speed of light. So therefore, its light can never ever reach us. So it remains invisible to us. Some astronomers believe that this whole observable universe that we can see, right, which is about 56 billion light years across, 56 billion light years across, it is just about 10 to 20% of our original universe. Our original universe, right, the real universe, which consists of the observable and the non-observable part, is huge. Our observable part is just about 10 to 20% of that universe. 70 to 80% or maybe 90% of our universe are non-observable areas. We can't observe it. So we do not know really how big this universe is. And this is just the first layer of heaven. We talk about seven heavens, 7 layers of heavens. This is the first layer of heaven, so huge. Just the observable universe is already mind-boggling. You factor in the non-observable universe, you can't even start to imagine, right? So the non-observable universe is because of the expanding universe, the edge here, right? All these quasars or far distant galaxies, right? In a distant future, its velocity will go beyond the speed of light. So therefore, it will jump into the non-observable part of the universe and it will be lost forever and ever. And if you calculate that, right, by logic, in far distant future, right, this whole universe will be empty. If let's say there's no kiamat lah, right, because stars will be extinguished and the stars at the fringe will jump over to the non-observable universe, and therefore it will be a very dark, sparse, empty universe, if the universe exists to that point. Right? Some astronomers believe that, but we Muslims, we believe that no, we not reach to that point. The whole universe will be destroyed by Allah subhanahu wa ta'ala, as how Allah subhanahu wa ta'ala created this universe. That is how this universe will end. It will collapse. It will not expand forever. Okay, so this is actually the explanation for the expanding universe. So we talk about expanding universe, is actually the space. It is not the velocity, the actual inherent velocity of the galaxies itself. No, the galaxies are fixed. It is not moving. How it was created billions of years ago, it is how it was there, fixed at that moment of, at that point of space. But because the space between these galaxies expand, so the galaxies are actually perceived to be moving away from us. Now, the fact is that space is expanding. It's not just space out there, it's the space everywhere. In fact, the space inside us. We are an object. We have space inside us, atoms. We are consist of atoms. And atoms have plenty of space. And that space is actually expanding. But why don't we explode? Why don't we get bigger and bigger and explode? Why is this earth remains like that and it's not getting bigger and bigger? If you say that space is expanding, so the space inside the earth is also expanding, and so therefore the earth must get bloated and then broken away, right? Exploded like that. Why is not so? Because there is another force in this universe that is called gravitational force. So this gravitational force is actually, right, pulling objects that are close together so that it will not expand. So gravitational force, right, overcome this force that caused the expansion of the universe. And that force that caused the expansion of the universe, or the force that caused the expansion of space, physicists theorize that it is caused by a particle called Higgs Boson. They've just discovered Higgs Boson actually. It was theorized in 1960s by this British physicist by the name of John Higgs, something like that. But Higgs, his name is Higgs. So he said, because of that, I call this particle as Higgs. Boson is a type of that particle. So then it remained just on paper in theory until quite recently they discovered this Higgs boson, this particle. And scientists believe that this particle actually caused the expansion of the universe. But because gravity is also strong, gravity pulls back the expansion for those objects that are close by, nearby, right? So planets, right? We are being attracted, compacted together by our own gravity, the Earth gravity. So therefore, Earth is not expanding, right? The expansion of the space inside the Earth is being cancelled by the gravitational pull of the Earth itself. So that is actually the reason. Now, if you look at this, right, like I mentioned just now, is our universe going to expand forever? We are at the moment where we are, for the scientists actually, right, we're not sure. I'm talking about the scientist perspective, right, the astrophysicist perspective. They are not sure. Is our universe going to be closed and it's going to expand and then contract back? Or is it a flat universe? It means that it's going to expand at uniform rate. Or is it an open universe? It means that it's going to expand at a greater rate. Which of these actually will be the fate of our universe, right? The current state of universe, whether it's closed, flat, or open. If it is flat or open, then it will expand forever and ever, right? The stars will be extinguished because there's no more elements. The elements will be scattered all over the universe, and the universe will become very, very dark. And some of the stars will jump over to the, what do you call it, the non-observable part of the universe, which is open or flat. But if it's a closed universe, then this universe will be destroyed. As how it began, it will be destroyed. So it expands, then the space expands, and then the space will stop expansion and will contract back. Why is it contract back? Because the total gravitational pull of all objects in this universe cause the expansion, right, to stop. So the gravitational pull of all the objects in this universe overcome the force of expansion. So the universe will contract and will be destroyed. Now, for the scientists, they are still not sure, right? But most of their data now points to the universe as being a flat universe. So it's going to expand forever. That is what current data shows, right, to the astronomers. But we Muslims, we believe that no, because the Quran says that kama bada'na awwala khalqin nu'idu, Allah subhanahu wa ta'ala says, as how we begin the creation, we will end it. As how we begin all the creations, we will end it. We begin, Allah subhanahu wa ta'ala create us as someone that is weak, and then we'll end up as a weak person. Allah create this universe, right, from a single point. So that's how the universe will end. It will end back into that single point. So if it starts with a big bang, then that will end up with a big crunch. That is how we believe in. But of course, the data right now does not point to that direction, no matter what, because the data is the current data. It can be changed. But our belief in our Quran cannot be changed. Our belief in our Quran cannot be subjected to current data, because Al-Quran is the truth, it's from Allah, right? It cannot be changed. It supersedes everything that we discover, right? Because our knowledge is limited. It is still expanding. What we know now as the truth, it might not be the truth in the future. What we know now as a fact, it might not be a fact in the future. But Al-Quran, as a Muslims, there's no argument about it. It is the truth. So we go back to the Quran, and for Muslims, we believe that the universe is going to be closed universe, not open, not flat. So if it's a closed universe, far, far in the future, right, the stars will get, the galaxies will get closer again, and all those objects, galaxies that are currently in the non-observable part of the universe will jump back to the observable part of the universe, and we get closer and closer, and the temperature will get higher, the temperature of the universe will get higher and higher, and everything will be destroyed. So it's just like the reverse of the Big Bang, right? So once we know about this thing, right, we're going to talk about Big Bang, the origin of everything. And then, inshallah, we'll talk in our next lecture, which will be next year. So, inshallah, I'll see all of you next year. Okay, so that's about it. Thank you very much. Let's see if there is any question in the chat. There's no question. Thank you very much. Okay, so we end our lecture tonight with Tasbih Kafara and Suratul Asr. Subhanakallah bika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Al-'asr al-insana fi khusr illa alladhina amanu wa 'amilus solihati wa tawassaw bil haqqi wa tawassaw bis sabr. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.